Hi, I'm Mark Barsamian. In this video, I'll be discussing approximating areas with sums. This material is from section 5.4 of the book, The Definite Integral. More specifically, from page 358 to the top of page 364, examples 1 and 2. The corresponding homework is this collection of exercises that are in the MyLab system. Some are from our book, some are actually from another book. Today we'll discuss a new idea. The idea is the area between the graph of a function and the x-axis from x equals a to x equals b. So a picture like this. We'll be interested in two kinds of area. One is what I'll call the unsigned area, and I'll abbreviate USA. This is what you would probably think of area in your life until now. It's the sum of the area of this green region, the area of this blue region, and the area of that green region. What's called the signed area is different. It's abbreviated SA for signed area, and it's computed this way: 1 minus 2 plus 3. That is, regions under the x-axis get a negative sign. So I've drawn the regions under the x-axis shaded blue, kind of like water, and the regions above the axis I've shaded green, kind of like grass growing on hillsides. So this quantity, signed area, may seem like a weird quantity to consider, but mathematically it's very important. We'll discuss it extensively for the rest of the semester. Today we'll consider examples of computing unsigned and signed area. And in simple examples, we can do this just using geometry. Example 1. Let f of x be minus x plus 11. Find the unsigned and signed areas between the graph of f of x and the x-axis from x equals 7 to x equals 14 by using geometry. All right, well, the solution to that is it helps to draw the graph. So the graph will be a line with slope m equals -1, and the x-intercept, of course, is at xy equals 0, 11, and the y-intercept will be at xy equals 11, 0, because this is a graph that has slope -1, and it goes through this y-intercept. So it's easy to see that you go down 1 over 1, down 1 over 1, you'll arrive at this point. Now, I've drawn the region that we're interested in, the region between the graph and the x-axis, from x equals 7 to x equals 14. And I've shaded the part of the region that's above the x-axis in green and the part that's below the x-axis in blue. So we need to find the area of those two regions separately. Well, the green region is a right triangle with base b equals 4. That's this distance. And height h equals 4. That's this distance here. So its area is found by the formula a equals 1/2 the base times the height. So you just get an area of 8. Now let's turn our attention to the blue region. The blue region is also a right triangle. Its base is 3. That's this little length. And its height is also 3. That's this little length. So when you use the same area formula, 1/2 the base times the height, you get an area of 9/2. Now, we use those numbers to find the signed area and the unsigned area. The unsigned area is the easier one, the more natural one. So it's abbreviated USA, and it's found by adding the green and blue numbers. So we add that number 8 to that number 9/2, and we get the result 25/2. That's the unsigned area. Now what about the signed area? The signed area will be green minus blue, so 8 minus 9/2, so the signed area is 7/2. Let's go on. Example 2. Let g of x be defined by this graph. This graph has part of a circle that's centered at 5, 1. So that's here. That's the center of the circle. Our job is to find the unsigned and signed areas between the graph of g of x and the x-axis on the interval 5, 8 by using geometry. And the task is to give an exact answer and a decimal approximation. Well, the solution to this is to note that the top part of the region is a quarter of a circle with radius r equals 3. So its area is going to be 1/4 of the area of a circle. So that's going to be 1/4 of pi r squared. So 1/4 of pi 3 squared. So in other words, 9 pi over 4 is the area of that green quarter circle. But that quarter circle is sitting on a rectangle. The rectangle has width w equals 3 and height h equals 1. So its area is 3. So the unsigned area will be just the sum of those two numbers, 9 pi over 4 plus 3. That's actually the exact answer. That's the only way to write that number exactly. You can't write that using a decimal exactly. You can't write it using a fraction exactly. Now, a decimal approximation to this we can get just by typing that into a calculator, and we get this number 10.07. Now that's both the unsigned area and the signed area because the entire region was above the axis. We've seen that for regions made up of simple geometric shapes, we can get the signed area using geometry, and of course the unsigned area as well. But what about regions that are not made up of simple geometric shapes? So for example, for the function f of x defined by this curvy graph we had earlier, let's consider these two questions about area. How do we define the signed area between the graph of a function and the x-axis from x equals a to b for a general function f of x whose graph is not made up of basic shapes? What do we even mean by the area? And how can we find the value of the signed area? So how do we define the area and how do we find its value? The first question might seem a little strange. I mean, how do you define the area? But if you think back to your experience in previous courses, you probably never encountered a definition of what area means. Rather, you just had various formulas for computing the area of basic shapes and rules for computing the areas of more complicated regions that were made up of basic shapes. It may seem like we would have to answer that area question number 1 before answering area question number 2. That is, it seems like we would have to have a definition of what we mean by signed area before we could have any idea of how to compute its value. But it turns out that we can fumble our way to an answer to question 1 by first trying to answer question 2. That brings us to the idea of approximating areas with rectangles. Our quest to answer those area questions will begin by considering area question 2. How do we find the value of a signed area between the graph of a function f and the x-axis from x equals a to x equals b for a general function f of x whose graph is not made up of basic shapes? Well, we'll consider doing this for a particular choice of f of x and an interval ab. We'll try to find the value of the signed area between the graph of this function and the x-axis from x equals 2 to x equals 12. So that's shown here in this picture. Remember, we haven't yet defined what signed area even means for such a region. That's what we're trying to figure out. But we can formulate 2 requirements that we'll ask of the definition of area when we finally come up with one. So here are the requirements that we want a definition of area to satisfy. The first is called positivity. For any non-empty region called R above the x-axis, the area of region R should be a positive number. That's reasonable enough. The other requirement is one you might not have thought of before, or at least not explicitly. It's called additivity. If you have some region R and it's made up of the disjoint union of regions A and B, then the area of region A plus the area of region B should equal the area of region R. So that could be drawn this way. Now, I haven't drawn regions involving a graph of a function in the x-axis. I'm just drawing areas of curvy shapes in the plane. Now, as a result of positivity and additivity, it'll be true that if some region A that's above the x-axis is entirely contained in some region R above the x-axis, then the area of A should be less than the area of R. That idea can be used to give an upper and lower estimate of the signed area of the blue region above. Remember, we're trying to give an estimate of that area. So consider the green, blue, and red shaded regions in this figure below. We don't know the value of this signed area. That's the thing that we're trying to find. We haven't even defined what that signed area means. But the green and red regions are made up of rectangles. This is a bunch of rectangles. That's a bunch of rectangles. So we can find the signed area of those regions. Then we'll have lower and upper bounds for the unknown and not even defined blue region. So you can see that this green region is entirely contained in that blue region. So that green region's area should be less than the blue region's area. And that blue region is entirely contained in the red region. And so the blue region's area should be less than the red region's area. I like to think of this as sort of an area sandwich. So that's the idea of approximating areas with rectangles. We'll now set about computing the green and the red areas, and we'll do it in a way that the process can be generalized to other examples. The terminology that will be introduced to is that of left rectangles, left sums, right sums, and more generally, what are called Riemann sums. So first, left and right rectangles. For a given function f of x, we're going to define left rectangles and right rectangles as follows. A left rectangle sits on the x-axis and is the correct height so that it touches the graph of f at the rectangle's left corner. So there you see the rectangle's left corner touches the graph. The definition of a right rectangle is that it sits on the x-axis and it's the correct height so that it touches the graph of f at the rectangle's right corner. So you can see that this red rectangle touches the graph at the rectangle's right corner. Now, a remark is in order. These definitions sound simple enough, but notice that if the graph of f of x is below the x-axis, then the rectangles will have to go down to touch the graph. And if the graph of f of x happens to have an x-intercept, then a rectangle may have no height at all if its corner happens to occur at that x value. Now I want to talk about what are called left and right sums. A left sum will be defined to be a number that is obtained by adding the areas of a bunch of left rectangles in a certain way. So the symbol for left sum will be this, capital L subscript n, and it's spoken the left sum with n rectangles. Now you use this symbol when you have a continuous function f of x and an interval a comma b, a closed interval, given. Now what does that symbol L subscript n mean? What is the left sum with n rectangles? Well, what it means is this. You put n equal width left rectangles on that interval from a to b. You add up their area, and the resulting sum is denoted with that symbol L subscript n. So here's a picture of a left sum, the picture of the rectangles that would be used to compute L subscript 5. Notice that there are 5 rectangles in that picture. Each one of those rectangles is a left rectangle. Each of those rectangles touches the graph at the rectangle's left edge. And those rectangles are sitting on the interval from 2 to 12. And they're equal width. Similarly, for the definition of a right sum, denoted by capital R subscript n, spoken the right sum with n rectangles, you use that symbol in the same sort of situation. You have a continuous function f of x, and an interval a comma b, closed interval, given. And what this symbol means is the following. You put n equal width right rectangles on that given interval. You add up their area, and the resulting sum is denoted by that symbol, capital R subscript n. So here's a picture of the 5 rectangles that would be used to compute R subscript 5 for that function, capital F of x equals 5 plus x squared over 10 on the interval from 2 to 12. Notice that each of these rectangles is a right rectangle because each rectangle touches the graph at the rectangle's right edge, and those rectangles are equal width, and they're parked on the interval from 2 to 12. Now I want to talk about Riemann sums. The left sum and right sum are just 2 examples of a whole family of sums called Riemann sums. They're named for German mathematician Bernhard Riemann, who lived 1826 to 1866. Riemann was an important figure in the development of the theory of the integral. Now I want to talk about computing left and right sums. We'll compute one example involving a particular function f of x and then present the general procedure. So example 3 is to find the left sum and the right sum, each with 5 rectangles, for this function f of x equals 5 plus x squared over 10 on the interval 2 to 12. That is, find the values of L5 and R5. Well, the regions corresponding to L5 and R5 each have 5 rectangles. To compute their areas, we'll need to know their widths and their heights. So let's start by thinking about the widths. The rectangles are going to be parked on the interval from 2 to 12. There are going to be 5 rectangles, so they're all going to have the same width, which is going to be w equals 2. That width is obtained by dividing the width of the whole interval by the number of rectangles. So I got 2 by doing this calculation. 12 minus 2, that's the width of the whole interval, divided by 5. More generally, that's b minus a over n. Little b is the right endpoint, and little a is the left endpoint. For the sake of generalizing this procedure, it's helpful to name the rectangle width and to make note of how it's computed in general. So the symbol for the rectangle width will be this, delta x. Remember, delta is often used for change in. So change in x, or rectangle width, delta x, is computed using this formula, b minus a over n. Now we need the heights of the rectangles. The heights of the 5 left rectangles are the same as the height of the graph of f of x at the left edges of the green rectangles, because those are left rectangles. Those left edges are located at the x values 2, 4, 6, 8, 10. On the other hand, the heights of the 5 right rectangles are the same as the height of the graph of f of x at the right edges of the red rectangles, because those are right rectangles. Those right edges are located at the x values 4, 6, 8, 10, 12. So notice that there are overall 6 important x values involved in computing the heights of those 5 left rectangles and the 5 right rectangles. For the sake of generalizing this procedure later, it's helpful to name those 6 important x values and observe how they're computed. So what I will call x subscript 0 is the x value at the far left end of the interval. That one. That is my x equals a. The value of a is the x coordinate of the left end of the interval. And then the x values get denoted x1, x2, x3, x4, x5. So a total of 6 x values. And notice the rightmost endpoint of the interval is this number b, and it has the value 12, and it's denoted by the symbol x subscript 5. The leftmost endpoint, the number denoted by the symbol a, has value x equals 2, and it's denoted x subscript 0. All those other x values in between have their names. x3 is the number 8. for instance. And you can see how they're computed. You just start by assigning x subscript 0 to be the value of a. And then you just add delta x. So 2 plus delta x would be 2 plus 2. That gives you 4. That's the next endpoint. And then 2 plus 2 delta x, that is 2 plus 2 plus 2 gives you 6. So that gives you the x-coordinate of the next endpoint. Now what about the heights of the rectangles? The heights of the 5 left rectangles will be these 5 y values, f parentheses 2, f parentheses 4, all the way up to f parentheses 10. On our graph, those are these lengths. This length is f parentheses 2. This length is f parentheses 10. They're heights of those rectangles. The heights of the 5 right rectangles will be these 5 y values, f parentheses 4, f parentheses 6, all the way up to f parentheses 12. So on the red graph, those heights are these heights. F parentheses 4 is this height, f parentheses 12 is this height. So we see that it's going to be necessary to compute the y values at all 6 of those important x values that are listed. So starting with f parentheses 2, f parentheses 4, all the way up to f parentheses 12. Now remember the formula for our function. That's the formula for our function. Let's remember the empty version. There's the formula for our function, and that's what's used to do these calculations. You just simply plug those x values into that formula. For the sake of generalizing this procedure later, notice that those 6 y values can be denoted this way. We denoted them f parentheses 2, f parentheses 4, and so on, all the way up to f parentheses 12. But remember that those x coordinates, 2, 4, 6, 8, 10, 12, had names. They were x0, x1, x2, and so forth. So those y values are f of x0, f of x1, and so forth, all the way up to f of, this should say f of x5. Finally, we compute the sums. The left sum, L5, will be the sum of the areas of the 5 green left rectangles, with each area being a height times a width. The 5 heights are these numbers we computed on the previous page. The widths are all delta x equals 2. So this number, denoted L subscript 5, is height times width for the first rectangle, height times width for the second rectangle, all the way down to the final rectangle. The rightmost rectangle is the 5th rectangle, its height times its width. Now notice that each of those terms, each of those areas, height times width, has a common factor. They all have the same width, 2, 2, 2. Every one of those terms has a 2 beside it, so that 2 can be factored out, put at the very end. So now we have this expression that is the sum of all those y values times 2. Now we just use those y values from the previous page, these y values that were obtained just using arithmetic, and we get, finally, the number 94. So we've found a value for the left sum. L subscript 5 is the number 94. The right sum, R subscript 5, will be the sum of the areas of the 5 red right rectangles with heights f4, f of 6, f of 8, f of 10, f of 12, and widths are all delta x equals 2. So we build an expression for R subscript 5. It's the area of the first rectangle, a height times a width, the area of the second rectangle, height times a width, and so forth, all the way up to the 5th rectangle, height times a width, all added together. We can factor out the common factor of 2. Each of those rectangles has a width 2, so that number can be factored out. Then we use the y values that we computed before. We have all these y values. We're going to use that batch of y values this time. When we do that and just do all the arithmetic, we end up with that number, 122. So we found a value for the right sum. R subscript 5, that symbol stands for the number 122. For the sake of generalizing this procedure later, notice that the sums turned out to be this form. L subscript n was this sum. The sum of all those y values for that particular batch of x values times delta x. And for the right sum, Rn was this sum, the sum of y values for a slightly different batch of x values times that width delta x. Notice again that in computing the left sum, we used these y values. In computing the right sum, we used these y values, slightly different batch of y values. These sums can be abbreviated using what's called summation notation. Now, you've been exposed to this at some point in the past in one of your courses. We will not use this notation in our course, but it's interesting because it'll be the inspiration for a symbol that we'll be introduced to later. So that expression for the left sum can be abbreviated using this summation symbol. Remember what this symbol means. It means add up a bunch of terms that look like this. Each of those terms is a height times a width. That's what we did in the very beginning before we simplified. Remember, in computing L5, we did that term, height times the width, plus that term, height times the width, all the way up to this term, height times the width. Now, each of those terms has a label. It's computed by finding a y value at a particular x value, and you indicate which batch of terms you're adding up by these what are called indices. The value of k starts at 1 and goes to n, and this big symbol is the Greek letter capital sigma, which indicates that you're supposed to add up all of those things that look like that. So you're adding up a bunch of terms that look like that. The right sum, which was expressed with that expression, remember that was a sum of a bunch of terms that look like this, very similar, a height times a width, and these indices indicate where you begin and where you end your list of terms that are going to be summed up. So again, we won't use this notation, but in a little bit we'll see that it actually is the origin for a very interesting symbol. Now let's discuss our results. We found that L subscript 5 was 94 and R subscript 5 was 122. Now remember our picture illustrating how we were going to find lower and upper bounds for the area of the region between the graph of f of x equals 5 plus x squared over 10 and the x-axis from x equals 2 to x equals 12. So this was the region whose area we would like to know. We don't have a way of computing that. We don't even have a definition of what that area means. But we know from the idea of the positivity and additivity that that blue area, that signed area, whatever it is, whatever it means, it ought to be greater than the value of L5 because that green region is contained in that blue region, and the value of the blue signed area should be less than R5 because that blue region is contained in that red region. So now we see that there are actual numbers that we can list as bounds. The signed area that is unknown, that blue signed area, is somewhere between 94 and 122. Now, aside from the lower and upper bound, that the signed area is between 94 and 122, what else can we say? Well, not much. I mean, you might want to guess that maybe that area will be roughly halfway between those green and red areas. So you might want to guess that maybe the signed area is around 108, but you don't really know. All you know is that that blue area is greater than 94 and less than 122. Now, the example that we just finished was very long, but along the way we made note of the important steps in the solution, and we wrote formulas showing how those calculations for those steps could be generalized. We put those formulas in some green boxes, like that. And that. And the x values were listed in this green box, and so forth. Well, the whole procedure can be summarized succinctly into a 3-step process by simply gathering up the formulas in those 4 green boxes and repackaging them in one. I'll show that procedure on the next page. So these are the steps for computing left and right Riemann sums. Given a continuous function f of x and an interval a comma b, step 1 is to compute the rectangle width. Call it w, or delta x. You compute it using the formula b minus a over n. Step 2 is to make a list of the x-coordinates of the edges of all the rectangles. And remember, that list is going to have n plus 1 numbers on it. Starting with x subscript 0, which is the x-coordinate of the left end of that given interval. And the last x value on the list will be denoted x subscript n. And it's going to be the value of b, that's the right end of that interval. And the x values in between are spaced apart, equal spacing. The spacing between them is this number delta x. So you make that list of x coordinates, and then you find the corresponding y coordinates at each of those x values. So you end up with this table of x values and then the y values at those x values. And then step 3 is to use the y values on the list and delta x to compute ln and rn. ln is computed using this batch of y values added up together times delta x. Rn is computed using this batch of y values added up together and then multiplied by delta x. Now I want to talk about getting tighter lower and upper bounds. In example 3, in our picture showing the region between the graph of this function and the x-axis on the interval 212, along with the rectangles for L5 and R5. Let's go back and look at that picture. This picture. Notice that there are sizable gaps between the rectangles in the graph of f of x. Gaps there, there, there. So the green region is smaller than the blue region because of those gaps. And the red region is larger than the blue region because of these gaps that are filled in gaps. That's why our lower and upper bounds of L5, which is 94, and R5, which is 122, it's why they're so far apart. If we used more rectangles, skinnier rectangles, we could eliminate some of that empty space, and our lower and upper bounds would be closer together. We'll do that in our next example, and we'll use a computer to do the hard work. So in example 4, we'll find better lower and upper bounds for the unknown quantity that's the area of the region between the graph of this function and the x-axis on the interval from 2 to 12. We abbreviate that SA for signed area. We'll find these better lower and upper bounds by computing the left sum and right sum with n rectangles. That is, find the values of L subscript n and R subscript n with higher and higher values of n. To compute the left and right sums, we'll use the Riemann sum calculator on the GeoGebra website. Now this link is actually not working. It's not an active link in the notes for this drawing program. So I just have this website open. There's the calculator. We'll present the results in a table with a column for L subscript n and a column for R subscript n. Now remembering that these will always be lower and upper bounds for the unknown value of SA, the signed area of that blue region, we'll include a column for this unknown quantity. We'll show the results from example 3 in the first row. So here's the table. Left and right Riemann sums for this function on this interval. In the first row of that table is the information that we got in our previous example where we did the sum by hand. We found the left sum was 94, the right sum was 122. That told us that the signed area, the unknown signed area, that blue region, was somewhere between 94 and 122. Now let's focus on this row of the table. When n equals 10, let's see if we can get these values. L subscript 10 is 100.5, R subscript 10, 114.5. Let's see if we can get those values by typing this information into that Riemann sums calculator. Now you see that Riemann sums calculator page. I don't have a way of writing on this page. Maybe I can move my cursor. You can see that I've typed the function 5 plus x squared over 10 in this box, and I've typed the endpoint a equals 2 in this box, and b equals 12 in this box, and the number of intervals 10 in that box. And you see that the answer is the left sum is 100.5. And you can see a picture of this sum. All these rectangles are left rectangles. Every one of those rectangles touches the graph at the rectangle's left edge. The value is 100.5. Now let's switch and show the right sum. The right sum has value 114.5. You can see that each of these rectangles is a right rectangle. They touch the graph at the rectangle's right edge. So we have confirmed these values. Now let's see if we can do the left and right sums with 1,000 rectangles. I'll simply change the value of n to 1,000. So there you see that the rectangles have gotten so small, so skinny that you can't see the gaps. The value of the left sum is 107.2634. The value of the right sum is 107.4034. So we've confirmed this row of the table. I won't do any of the other rows. Let's look at the trends in this table. Notice that the values of n are getting larger and larger positive without bound. That could be denoted n arrow infinity. N is going to infinity. Now look at the values of the left sums. They seem to be getting closer and closer to around 107.33. Now look at the values of the right sums. They seem to be getting closer and closer to around 107.33 as well. Now keep in mind that in each of these rows we have an area sandwich. That blue signed area, which is unknown, is somewhere between the green number on the left and the red number on the right. This blue number in the middle is not changing. It's just some unknown number. But it's always in between the green and red numbers. Now, based on this table, we can see that that unknown blue number and an undefined blue number, which we've denoted SA, that number that's the value of the area of the region between this graph of this function and the x-axis on the interval, that blue area must be around 107.33. And that's the end of that example. Now let's make some observations about this example. First observation is that, of course, higher values of n allow us to give better and better estimates. So for instance, based on, this should say n equals 5. Based on the first row of the table, that's the row of data that we got from example 3. That row of numbers was computed by hand in example 3. Remember that at the time we discussed what that told us about this unknown value of the signed area. Based on these numbers, the left sum is 94, the right sum is 122. Based on just that, the best we could guess about the unknown SA was that maybe it's around 108. If we wanted to just guess that it's maybe midway between 94 and 122. But based on the n equals 100 row of the table, we could give a better estimate. If you look at that row of the table, that unknown blue number is sandwiched somewhere between 106.6 and 108.0. So we might guess that based on that row, maybe that unknown blue number is around 107. But if you look at the n equals 10,000 row of the table, we might guess that the signed area is around 107.33. That n equals 10,000 row, the unknown blue number is somewhere between 107.32 and 107.34. So a good guess would be that maybe the unknown number is around 107.33. Another observation. The area sandwich won't always occur. Notice that in every row of the table, we have this inequality. The value of the left sum is less than the signed area that we're trying to find, and that's less than the value of the right sum. That's what I called the area sandwich, and it's illustrated by this figure. Now realize that that inequality occurs because the function f of x equals 5 plus x squared over 10 is increasing on that interval. If instead we are dealing with a function maybe called g of x that was decreasing on that same interval, we would have reversed inequalities. The left rectangles, the ones that touch the graph at the rectangle's left edge, now enclose this green region that's greater than the blue region. And the right rectangles, the ones that touch the graph at the rectangle's right edges, those rectangles make up a red region that's smaller than the blue region. So in the case of this picture, where the function g of x is decreasing, we would have this reversed sandwich. And in general, if we're dealing with a function maybe called h of x that's not strictly increasing or decreasing, there might not be an area sandwich at all. So we won't be able to predict the relative sizes of the left sum, the right sum, and the unknown signed area that we're trying to find. Now this might seem discouraging because we wanted to use the Riemann sums to find a value of the unknown signed area. And a key part of that was that the Riemann sums provided lower and upper bounds because of the area sandwich. So it seems like if we don't have the area sandwich, this whole plan sort of fails. But luckily, it turns out that one does not need the area sandwich. There's a big fact from higher math. This is the sort of thing that the mathematician Riemann proved. It's a fact that for a function f of x that's continuous on a closed interval, a to b, the values of ln and rn always approach some common number as n goes to infinity. That is, if you have a continuous function f of x on a closed interval, then this limit, the limit of ln as n goes to infinity, and this limit, the limit of rn as n goes to infinity, both those limits exist and they're equal to each other. The value of the right limit equals the value of the left limit. Let's go back up and look at our table. In this example, the values of the left sums were getting closer and closer to this number. So we would say that the limit of the left sums is around 107.33. And the values of the right sums were getting closer and closer to this number. So it would look like the value of the right sums is around 107.33. So again, the big fact is the limit of the left sums as n goes to infinity equals the limit of the right sums as n goes to infinity. Well, that big fact gives us a way to define the signed area of the region between the graph of a general curvy function and the x-axis on a closed interval AB, and also to compute its value. So that answers both area questions at once. Remember, the area questions were, how do we define the area between a curvy region and the x-axis, and how do we compute its value? Well, we can just define the signed area to be the number. That's the limit of those Riemann sums. That as we define that unknown blue area, here's a definition. We're going to say that it's defined to be that limit, which is also the value of that limit. So again, that answers both of our questions. How do we define the signed area, and how do we find its value? Now, because that definition of signed area is so important, it answers both questions about area. That definition of signed area is incredibly important. And because it's so important, it gets a name and a symbol. So here's the definition of what's called the definite integral and signed area. So the words are the definite integral of f of x from x equals a to x equals b. The symbol is this thing, which looks like our symbol for indefinite integral, except there are these things decorating that big curvy S-like symbol. There's an x equals a at the bottom of that symbol and an x equals b at the top of that symbol. Another way of saying this, instead of saying the definite integral of f of x from x equals a to x equals b, another way of saying it is this: the signed area of the region between the graph of f of x and the x-axis on the interval a comma b. And another symbol is just simply SA. That's my symbol. Nobody else uses that, but it's a nice symbol. Now remember, all this stuff we've been talking about is stuff that you can do when you have a function f that's continuous on some closed interval a comma b. So we've got these new words, the definite integral, this new symbol, and these alternate words and this alternate symbol, and what it means is the number that's the value of that limit, which is also the value of this limit. That is, this thing, this signed area, which is denoted by that crazy new symbol, is defined to be that limit, the limit of those left sums, which is also that limit, the limit of the right sums. Now I want to remark on the symbol. We've defined signed area to be the value of a limit. We can focus on the limit of just the right sum. So signed area was defined to be this limit of the right sums. And remember, earlier we had that abbreviated way of denoting the right sum. It was that summation symbol. The Greek letter capital sigma, that was denoting that we're adding up a bunch of things, and then the little delta x, which was the common width of all those rectangles. Now the symbol chosen for the definite integral is meant to signify that the definite integral is a limit. The large S-like symbol, this thing, is meant to evoke kind of a smoothed out Greek letter sigma. So that thing sort of smoothed out becomes this curvy thing. And then the dx symbol is meant to evoke a kind of smoothed out delta x. So this delta x that appears in the sum gets replaced with this dx. Again, this symbol is meant to remind us what this symbol stands for. It stands for the idea that you start with this sum, you take its limit, and the resulting limit is denoted by this blue symbol. Now, there's another big fact. We started the whole discussion today with a couple of examples of computing signed areas for graphs given by simple geometric shapes. Well, the good news is that this new definition of signed area involving the limits of these sums gives the same answer as doing the signed area using geometric area formulas. But this is still a little puzzling. We've only seen one example of this definition in use. In that example, we had to use a computer to find Ln and Rn for particular values of n as n got larger and larger, and we guessed at a rough value for the limit. We used a computer to get all these values, and we just guessed values for the limit. So there are a couple of obvious questions. First question is, can we do these Riemann sums analytically, obtaining general formulas, instead of having to do repeated calculations of y values? That is, can we just get a formula that will give us the value of Ln and Rn instead of having to crank out 10,000 y values by hand or by computer? Well, the answer to that question is yes. For most functions f of x, it's possible to obtain formulas for the sums that give Ln and Rn. But the bad news is the math involved in obtaining those formulas is above the level of Math 1350. Not too far above the level. Some of the techniques are discussed in the more advanced calculus course, Math 2301, but only for some simple cases. More advanced math courses still are needed to discuss more difficult, more general sums. So again, the answer to that question is sort of yes. It is possible to compute formulas, to find formulas that'll give the values of those sums, but it's above the level of this course. That's one question. Another question is, can we figure out the limit? That's the limit as n goes to infinity of Ln. Can we figure out that analytically without having to use a computer to find Ln and Rn for larger and larger values of n? Well, the answer to that is also yes. If we had the general formula for the value of the particular Riemann sum, Ln or Rn, the formula mentioned above, the idea that it is possible to get formulas that give you the values of these sums. If we had such a formula, then we could find its limit. Use that formula, find the limit of that formula, and you'd have the value of the signed area. We would use our limit laws to do that. So neither of those answers is very satisfying for us in Math 1350. We'd like to be able to find the value of definite integrals using analytic techniques at the level of our course. So the question is there an easier way to compute definite integrals analytically? That is, for a general function f of x whose graph is not made up of basic geometric shapes, we want an analytic way to find this signed area. It's denoted by that symbol. It's defined to be this limit of the left sums, which is also equal to the limit of these right sums. So we want an analytic way to find that. But the computation of those limits analytically depends on finding formulas for the Riemann sums that give Ln and Rn. And that's something that's beyond the level of this course. So what do? That's our question. Is there another way, an easier way, to find this value? Well, the answer to that question we'll see in the next video. That's the end of this video. Thank you.